kind of go through the first set of slides. And if I get far enough into the slides, this Friday may be our Friday that we take off right there. So that's there. Normally I would say 45 minutes. I'm getting close to the end of my lecture time, but since this is my only class for the day, I'm going to continue going and see whether or not I can get the first week's of slides going right there. So, right there. And I will post these slides on the Facebook page right there. So, that's there. Okay. Right there. I have no idea. I've not looked at these slides very carefully. They're a new set of slides that there, but this is Introduction to Computers, Internet, and the Web. So it's really not part of programming that there. This is kind of a background. This is for a new edition of the book. Actually, the edition of the book you're going to get is the 7th edition. So it's actually that there. So I taught this last semester using C++. I'm going to drop back to C. I just found that C++ for the level of students that we're dealing with here for introductory course was a little too cumbersome. So we're going to just use standard C right there. So in this chapter, and again, you haven't read the chapter, the book will be up before the end of the week. That there. So, that there, just scan it. That there. But basic computer concepts, different kind of languages, history, the purpose of standard library, a typical C program environment. And we won't test drive a C application that's there. So, but yeah, we'll see. I might do a quick demo. That's it. Yeah, that's it. And as you see, there's a whole bunch of stuff that there in this chapter. We'll jump over most of them fairly quickly. That's it. There's 2 pages of outline for the chapter, right there. So the core of the book is emphasizing software engineering. Again, I have used this pen in a while. Okay. Right there. Okay, so again, we're not going to be making you into software engineers, and why is it not, I'm supposed to be able to write. Okay. And my pen is not working. I see it work. The pen is working. The software is not working. Okay, well, that's all right. That's there. We'll see if the highlighter works. Oh, that's right. Ever since they changed this projector, the screen and the projector are, when I draw here, it sees it down there. So my pen is worthless in this class, in this room right there. It's a function of the projector and the screen resolution. I'm hoping that the Surface 5, when it comes out, fixes that problem right there. Okay, yeah, because even the mouse doesn't want to work right there. All right, well, I'm going to be working without the benefit of the pen right there. All right, so getting back to right there. Again, as I mentioned, this is Introduction to Software Engineering. That there, this is your only course in computer programming. Now, if you take microprocessors, you'll be doing some programming. And in the microcontroller course, which I don't teach a microprocessor course anymore, but the microcontroller course, I've actually changing that course to use Raspberry Pi, and there'll definitely be some Linux and some programming in that. And I'll probably introduce Python, which is a new language, right there, to totally confuse people. That's there. So, that's everybody. There. So we're going to learn how to write commands to learn how to command computers and perform certain tasks. That's there. So software is a set of instructions right there. A program is something you're telling the computer to do right there. Computers can perform calculations and make logical decisions faster than most human beings. That their computers can't think, but they can make decisions based on criteria in which we give the computer program. Now, when we talk about artificial intelligence, we're training the computer, the thought process, but it still follows a set of instructions right there. But computers can't, on their own, look at a set of data and make a decision right there. Yeah, I could read a newspaper article, pull out the facts, and use a thought process that I've developed over my 60 years of life and decide what, make an opinion or make a decision based on that there. I can look at the stock market, see what it's doing, look at historical data, look at various companies, that there and what their background is, read their financial reports, so I can decide whether or not I want to buy their stock. I can look at two candidates, their speeches, their track records, and decide which candidate I want to vote for. Except for Trump, which, everything he opens his mouth is a lie anyway, so that's recorded. Trump is noted for spewing alternate facts. They actually came up with a term for it. They call it alternate facts, which basically means lies, right there. So some politicians are noted that there's an old saying goes, how do you tell when a politician's lying? And that's when his mouth is moving. That there. So, and I don't know. I won't say anything about Malaysian politics, but I'll pick on the American politicians. And they did some analysis of Trump's statements in a normal speech and determined that about 70% of what he said was untrue. So 70% of the time he's talking, he's not knowing what he's talking about. That's there. So Hillary Clinton, when she was in the debates, they found about 30% of what she said wasn't true. But again, they could be because she's guessing and making that they're not delivering. Trump just doesn't know. He's just ignorant about the facts of life. Hillary is a politician. She tells people what they want to hear sometimes. Right there. So, and actually the other guy that was running against Hillary, they found that he was truthful about 90% of the time. But because he was truthful, he didn't tell people what they wanted to hear, so he didn't get elected. But regardless, that's a side note. But computer programs can look at a bunch of data on a preset criteria, make decisions very quickly, right there. They can perform billions of calculations in a second. They are very fast at processing data. Supercomputers can do thousands of trillions, quadrillions, of data processing that's there. This is important that computers can process data very quickly because everybody likes to use their cell phone, right? Your hand phone. Well, if computers weren't gathering that audio data that you were speaking into the microphone, converting that to digital, compressing it very quickly, and sending it in packets over the airway, routing it to the correct phone that you're trying to talk to, you couldn't do it. Cell phones would be completely out of the cost realm of the average consumer. I remember the old cell phones back when they were analog, and first off, they were considerably more expensive. They were also a whole lot larger, and they didn't do anything but make phone calls right there. And the phone call quality was not that good. The reception areas were not that good. So by computerizing the cell phone, you can now have a very reliable system that not only allows you to take your cell phone and have conversations, which, you think about it, that was the only purpose of a cell phone 10 years ago. But now you can put your Facebook page on that there. You can send text messages. You can take pictures and send pictures of your newborn nephew to your friends. That type of stuff instantaneously. Out there. And computers allow us to do that there. So computer programs under a control set right there. I like to look at a computer program as a recipe. The ladies are probably better at following this than the men, but your mother gives you a recipe on how to make nasi lemak, right? And so you know the first thing you do is and I don't know, I'm gonna probably give the wrong recipe, but you take coconut milk and you mix it in with water and you put the rice, you put a pounded leaf in it, and then you put it in the microwave for 20 minutes. That's there, or at least that's the way it, in my microwave back in the States, for 20 minutes. And you come out and then there's your rice, you make your sambal, you put whatever you want into the cuttlefish or squid or whatever that's there, and you have a series of sequence that you follow to make the nasi lemak, right? You do one thing out of sequence, like put it in the microwave before you add the water, it doesn't work. The order is important. Same thing for the guys. You're going to change the oil on your bike, right? You have a series of steps that you have to follow. You have to remove the oil plug, drain the old oil. If you're going to rinse it out, that's there. Although most people don't do that when they change the oil, but that's there. You replace the oil plug and you put the new oil in, and that's there. I never change oil on a bike. I changed it on cars, but I've got a bike now and I take it to the shop and let them change the oil. But regardless, you've got a series of steps to follow. And let's say you did something, you left a step out, or you did the wrong sequence. You put the new oil in before you replace the drain plug. What happens to that new oil? It goes on the ground, right? That's it. It doesn't work. So computer programs are a series of instructions you want the computer to follow right there. And sometimes we want them to repeat a series of instructions, that's it. So, you keep repeating for each and every student in the class how you calculate their grade point average right there. So we have a way of writing instructions for the computer program. That's all software is we're telling the computer what we want it to do right there. You've already done this when you've done other things. If you cook a recipe, you're going to make a new dress right there. You buy the material, you cut the material, you sew it a certain way. You have to take measurements before you cut the material. There's a series of steps that you follow to make a dress, right? You want to replace the fan belt on your car or replace the engine in your car, which is a relatively large process. You have a series of steps you have to follow. And if you're smart, if you're going to replace the engine, you go out and you get the manual on it, and it tells you the steps one by one, because if you leave a step out, bad things happen, right? Same thing with computer programs, is that we're going to have to sit down and analyze what we want this program to do and write the instructions one by one. And that's what we do right there. So this kind of goes in the slide. Computers used to fill large rooms, cost millions of dollars decades ago. I mentioned my $30,000 hard drive. That's there. We had a computer when I was going to school. It was an IBM 370, which was a large computer. It took up about a third of this room. It had card punch readers. It cost roughly $1 million right there. I mean, these things were large, and they had big tape drives on them. Hard drives weren't invented. You had key punch cards that you wrote your programs on. That's there. Things are much quicker, easier, smaller, cheaper today. You could buy a Raspberry Pi for about 150 ringgits, 170 ringgits right there. And it's a full-blown computer, and it's the size of my wallet. Actually, half the size of the wallet's credit card size. I've got a couple of them right there, and I'll probably give a demo later, just to show what they look like right there. But it's a full-blown computer that's like, I would say 10 times more powerful than my first IBM PC, which I paid over 3,000 USD for. And now we're talking something that's roughly 35 to 40 USD right there. And my old PC, IBM PC, came with 64K of RAM, and a K, a meg is 1,000 K, a gig is 1,000 meg. So when we look at 64K, that's 1 millionth 64 gig. Now my desktop computer at home, I've got 32 gig. So that's 1 million times larger than 32K, which was a common size back when I bought my first PC. So my memory size is 1 million times larger, roughly, than what it was 30 years ago, 35 years ago. I think I bought that computer in '84, so we're talking 33 years ago. Memory sizes have grown by roughly 1 million to 500 million, or 500,000 times larger, for far less money. The Raspberry Pi comes with 1 gig. The 1 gig, most of your phones have got 1 gig to 3 gigs on them, depending on which model phone you've got. So memory has gotten much, much cheaper. Processors have gotten much, much faster. My old IBM PC ran at 4.77 megahertz. I just bought a new processor for my desktop, and it runs at about 4 gigahertz. So you're talking a processing speed going from 4.77 megahertz to roughly 4 point something gigahertz. I've multiplied the speed by 1,000 times. So I've got 1 million times the memory, 1,000 times faster, plus the data bus is larger. I'm processing 64 bits at a time. I use a processor, so I'm processing 4 times as much data every clock cycle. So my 1,000 times faster now becomes 4,000 times faster. And the price is much cheaper, right there. So Moore's Law, you'll still hear it today. There's all kinds of articles in the trade journals that say, is Moore's Law still relevant? And Moore's Law says that every year or two, the capacity of computers are going to double in expensive. So a processor or memory size in your phone today is probably going to double in 2 years. And if you look at a phone that's 2 years old, right there, you'll probably find that 2 years ago, it probably had 1 gig of RAM. The same model probably has 3 gig of RAM today, or 2 gig of RAM. It had a particular processor. This tends to be slowing down a little bit. And the reason it's slowing down has nothing to do with technology. It has to do with needs. How fast a computer do you need? Right there, does the average person need? Right there. On the upper end of high-end systems, I've got a fairly high-end system that I use. It's got an i7 processor, and as I said, I just put a new one in over the weekend. I had an i5 in that there, and I've got 32 gig of RAM. I've got a very, big machine that I record videos and I edit them. These here on this here I don't edit. I just post them as is. That there, I don't try editing videos with it. But that there. But the average person, like my wife, she's still using a computer that's 5-6 years old now. She's starting to complain about it when she sees mine. That there, she'll come in and see me do something and go, "Oh, yours is so quick, it's so quick. When are you going to upgrade mine?" That there. So if she hadn't seen mine, she would be very happy with hers. But so the need for people to upgrade their computer is not, and it's great. So PC desktop computer sales have plummeted over the last 3 or 4 years. That computer sitting there on your desktop, they don't sell many of those anymore. The number one sold computer today is the laptop, followed by the tablet, and probably the fastest growing is the hybrid computers. This is a hybrid. In other words, I pop the keyboard off and it becomes a tablet. I flop the keyboard on, it becomes a computer. That's my favorite platform today. But this is also the most expensive platform. So as you can probably guess, I spend a good portion of my salary on toys. At least that's what my wife says. That there, I buy a lot of toys. That there, and high end. But what have I done for the last 35 years is computer engineering type activities. That there, especially in the hardware side. So I've always had to use that there. And I got spoiled in my last job. I had a 27-inch i7 iMac that there, which was a super sweet computer. That there. It also cost 5,000 USD. So that there. So I don't have, my computer at home is not nearly as nice as that iMac, as much as I say that there. But that iMac was a sweet computer. So when you get spoiled like that. But Moore's Law has kind of slowed down a little bit. That's why a lot of people are asking is it still relevant. From the electronics side, that we can keep up with Moore's Law, but the market is not looking for a faster. What they're looking for is smaller. That there. So Moore's Law, that their hard drives have definitely doubled in size. You can buy a 10 terabyte internal hard drive for a desktop computer. You can buy, I think for a laptop, the biggest is probably a 2 terabyte. Those little the 2.5 form factor won't take the very large ones. Thumb drives. Well, look at what's happened with flash. Your little thumb drives. What do you call them? Your pen drives, thumb drives, flash drives. That's it. But you know what I'm talking about. The little external hard drive. A couple years ago, 1 gigabytes were considered big. Now they sell 128 gig hard drive or thumb drives. And I think I saw someplace. Well, actually, I just put it in here a little micro SD card that was 200 gigabyte. Right there. So you look at the doubling of space on flash drives. You can see Moore's Law is still in effect in some aspects of it. Not necessarily in processor speed. So in processor speeds, it's still going up fast because we're asking computers to do more things. Trust me, 5 years ago, you tried to watch a movie on a desktop, it was almost a painful experience. Forget on a phone or a tablet or something like that. So we're asking computers that their communications field, you look at how much data Maxis is running through their cellular network comparison to just 2 years ago, right there. Cost has plummeted at there. Malaysia, I buy prepaid. I don't make many phone calls, so I don't. But I buy a data plan for 30 ringgits a month for what? I think I get 2 gig of data for that or something like that. That's a lot of data for a cell phone, right there. So, okay, we've got basically our logical units. I'm just going to kind of go through that there. The input unit is how we input data into our computer. There's all kinds of things there, and I can't write on this here, but when we look at our data, let me try. That's going to be a pain. Let me see if I can use OneNote. Right there. Yeah, OneNote is right there. Okay. So I can at least, I can't write on the slides, but I can write on it. So it's there. But when I look at that there, when I look at our input unit right here, what we've got here is we've got our input. We go into our processor, and right here, I'm going to call this our CPU, Central Processing Unit, right there. And then we got our output, put right there. And then we also have right here, storage, right there. That's our hard drives, our thumb drives, that they're flash drives. Now a cell phone, you still have storage. It's just a flash drive within the cell phone right there. And then some cell phones have add-on memory cards. The Samsungs except for the Note 5 and the S6 allowed you to, except for, those Samsungs all allow adding external memory cards. For some reason, they took that away with the Note 5 and the S6, S5 and S6. And they brought it back with the S7. And they brought it back with the S7. Yeah, the Note 7, except for the Note 7 tended to blow up, right? Caught fire. Apple doesn't allow external memory cards, right there. And the reason is it allows them to sell bigger phones, right there. So, but those are our basic four, right there. And if we go back to my slides here, right here, they list here the input section, and they call other forms of input might include voice commands. I could hold the button on my Bluetooth headset for a couple seconds, and my cell phone will then come back and ask me to, Google Voice will ask me for a command that's there. So these are all various forms of input. Secondary storage I call hard drives, some drives. These are secondary. That they're a video camera is considered a input. The computer is there. The internet there. Now newer forms you can also tend to use accelerometers. You can use GPS. Those are all input devices right there. The output is your screen, your printer, your speaker, your monitor. Those are all various types of things right there. So other forms could use the vibration. That's there. You can feel your phone vibrate. That's an output device right there. So the memory unit right there, that's the secondary. They're showing the internal memory of the CPU. For this class, I'm not going to get too much into that RAM right there. That little block diagram I just showed right there, I'm not going to worry about. The RAM is in this right here. I wonder where the fifth unit you was talking about. Here's the RAM right there. That's part of the CPU right there. So, and I disconnected the keyboard, so now I gotta go back to right there. So again, the ALU is what does the calculations. That's the actual computer itself out there. For this class, it's going to be an Intel-based processor right there. It's actually, I don't know what these computers are. There might be i3s or i5s. I don't think they're i7s. They may even be old dual-core processors. These are all outgrowths of the old Intel 8085, 8086, 186, 286, 486, the Pentium 2, Pentium 3, then became the dual core, then the i3, the i5, the i7. But they're all generations of that same family of microprocessor right there. That's the ALU right there. So implemented as part right there, and that's the CPU. And so actually he's separated the ALU and the CPU. I grouped those together. So the block diagram I give is actually the simplest one. Input, output, processor, and then secondary storage. That's the one that I typically use. He uses a slightly different one. That's fine. That's there. But this is the key parts of it is really is that we've got an input, an output, we've got a processor in between, and we also have external storage right there. So our programs are actually fed into the CPU, and there are instructions from this to tell the CPU how to take the input, the data from the input, process it, and output right there. And sometimes the output is secondary storage, sometimes the input is secondary storage, sometimes the input's a keyboard, sometimes the input's a webcam, sometimes the input's a speaker or a microphone, sometimes the output is a file on the hard drive, sometimes it's data to be sent over the internet through a communications channel. We haven't got into that type of thing there. So multi-core, you'll hear this term dual core and quad core processors. Basically, that means that there's multiple CPUs on the same chip, which can be running different programs at the same time. Right there, they share the same memory, the same hard drive, same inputs, same outputs, so they're not 4 times faster. Right there. A lot of people would think that a quad core processor should be 4 times faster because it's going to run 4 programs simultaneously, but those same 4 programs have to share memory transferring space, they have to share. So from a hardware standpoint, they're not 4 times faster. They may be 1 or 2 times faster depending on what's going on. But out there. And sometimes actually Samsung, Apple has it. Samsung actually has what they call an 8-core processor. That they're octa-core. But in reality what it is it's 2 separate quad-core processors. And if it's in low power mode, the lower 4 cores operate. If it's in high speed mode, performance mode, the upper 4 cores operate. So it's one or the other. You're only using 4 cores at a time, but depending on what the phone's doing. If you're playing a video game on the phone that requires a lot of processing speed, then it's going to use the higher speed cores. If you're just checking your email over the internet, or you're just reading a PDF file or doing something simple with your phone, it's going to be the lower 4 cores that are going to operate. So it's not 8 cores don't function at the same time. So secondary storage, I've already talked about that. Hard drives, DVDs, USB flash players, right there. Can sometimes hold over 2 terabytes. Actually, the DVD players, the Blu-rays are up around 2 terabytes as far as space goes. The hard drives, you can have 5 terabyte hard drives, about the largest I've seen sold here. I've seen ads for 10 terabytes through U.S. vendors out there. In Malaysia, I haven't seen anything bigger than a 5 terabyte right there. So that 2 terabyte, even though these slides are dated, if you see at the bottom of the slide right there. Oh, this slide is dated 2016. It's interesting that the publisher used old slides as well. So this slide he updated in 2016 last year, and it's already out of date. So that gives you an idea of Moore's Law. When this slide was written last year or 2015, 2 terabytes were the largest hard drives. Now we're talking 10 terabytes a year or 2 later. So Moore's Law is that there. Right down here he says some hard drive desktops can hold up to 6. Now I'm saying I've seen 10. Right there. See, now the next slide is state copyright 2014. Right there. So these mixed slides around. Data process come from a data hard right there. Complex. Data can be simple or it can be very complex in the way we look at it. We can look at a list of, a simple data point might be the price of nasi lemak. Another data point might be how many orders, and the output might be the cost that you're going to charge the customer. Nasi lemak's 2 ringgits. I don't know. Can you buy nasi lemak for 2 ringgits anymore? 4 ringgits. Is that the going price? But let's say nasi lemak's 4 ringgits, and I walk up and I say I want 5 orders. So if it's 4 ringgits, I'm going to charge you 20 ringgits right there. And the output that you're going to tell the customer is 4 times 5. The number of orders. It's simple. It can be very complex right there. A model of vehicle can be extremely complex right there. So we can have one data point right there called a vehicle right there, and it can have the VIN number, which is the vehicle identification number. It can have a model right there. It can have a color. It can have engine size, and these are all sub data points within one vehicle's record right there. So right there. So again, what we get is we process from bits to characters to fields. So each one of those data points is a field. A bit is true or false, right there. A simple data, a data point might be sex, male or female, right? It's 1 if it's male, it's 0 if it's female, and that's not an insult saying that there. But if I want to identify the sex of a customer, I only need 1 bit, 1 piece of information, a 1 or a 0, right there. Active student, 1 or 0. He's either active or he's inactive. That's there. A grade might be something larger. It might be a number between 0 and 100, right there. A test grade. So that's again a relatively simple. So the simplest one is a bit. So male or female, active or inactive. Exam grade might be, an 8-bit number. 8 bits will allow you a number between 0 and 255. We'll get into that later. A vehicle might have multiple fields right there. So I could I could have 8 different data points to identify a vehicle right there. So that's it. So here we're getting into a data hierarchy where we've got, and again, Judy is the name, and I don't know if those are last names or whatever right there. And Judy is represented by a character, which is an 8-bit number right there. We'll talk about that later. And Judy has, as a string, has 5 characters in her name. So we've got a file, 1 record has 2 fields, and each one of these fields has a string, and each character in the string has a character to it. So, and we'll get into more detail how this works right there. So, again, bits are the smallest, it's either a 0 or 1. Characters, that there are every letter representative in the Roman style Rumi alphabet, or I normally say the English alphabet, but that also includes Rumi Malay, is represented by a character right there. Every letter has a character, and that's in the ASCII character set or the Unicode's character set right there. So Unicode actually is a little larger than the ASCII set right there. Fields, but there, again, a field is a group, and I already talked about fields like first name, last name, job title, pay rate, in a more complex data structure right there. And a record is a complete grouping of data that pertains right there. And we'll start talking about records toward the end of the class. A file is something you place on secondary storage. I can have a file with all the grades for this class where I list every student and their test 1 grade, test 2 grade, test 3 grade, lab 1, lab 2, lab 3, all the various grades that are supposed to be turned in. Although the way things work now, I'm going to keep grades simple because of the quality control reporting right there. So, because evidently if I assign a grade to it, it's included the grade, I have to go through sampling and all that stuff. So I'm going to keep the grades relatively simple. A database can have multiple files that tie to each other. A database would be like, for example, UniKL's student database would contain all the students in the database right there, and there would be various relationships between them. And I may have, for example, your student record, there includes a schedule, but then I have another file that contains all the students in my class, but then when I pull up your record, I actually am talking to the file with the students. They're tied together. So I'm tying different files together into a database. I've done database programming. It's very interesting, actually. It's not my favorite thing to do, but I can go through and I can sort through all the students in my class with passing GPAs, for example. So I go through each student in my class, I pull up their student record from the other file, and I look at their GPA and I print that out, saying these are the students that received that are A students, these are the B students, these are the C students, these are the ones that barely got through the other classes. And I can generate all kinds of reports right there. And databases are used for generating reports, that they're searching data. A lot of companies do a lot of work with databases in terms of customers, trying to look for new customers, if they're big data is actually massive databases. All the citizens of Malaysia is trying to squeeze them into one large database right there. So that's there. And then I can find, set up a set of criteria. All right, which Malaysian that are potential customers for this new version of Proton? That's there. I can search this database, and based on certain criteria, let's say I brought out a new version. Well, I won't use Proton. I use Peridua, and they just brought out the Axia last year, right? Now the Axia is a very small car, correct? It's also kind of geared more toward women drivers than male drivers. It's a cute little car. Women tend to go for smaller, cute cars, and I'm being sexist right there. And in the States, I might get sued by it for making that statement, but I find that more women drive the Axia than men. Is that a fair assumption? Is that observation true? So if I want to sell Axia out there and it costs me money to send promotional materials, maybe I might want to concentrate on women drivers, right? And then I want to narrow it down. I want women drivers between the ages of, say, 18 and 45 or 40, because once they reach 40, chances are they're earning more money and they want a little nicer car. So I want someone in their 20s in particular. We'll just say 20s. That there, we'll cap it off at 30 or 35, and so we're going to narrow down to women between 18 and 35. And then we're going to go through and we're going to see which ones are employed right there. Then we can look at their salary if we got that database, and their salary is between, say, 4 and 7,000 ringgits per month. If they're making more than 7,000 ringgits a month, they can afford a nicer car. They probably don't want an Axia. If they're not earning 3,000 ringgits a month or whatever my bottom figure was, they can't afford to buy a new car. They're going to be buying secondhand cars. So I can go through and narrow down who I'm going to send these flyers to and save money. That's there. I may put the ads out that everybody sees, but I can target my advertising to a particular segment of the population right there. And that's what big data is all about. And trust me, companies like Facebook, they're selling your data. They are selling that data big time. That's how Facebook makes their money. Because you don't pay to use Facebook, right? That's there. They're selling a little advertising, you see, but what they want to know is how old you are, where you live, what type of friends you have, what religion you are, what type of job you have. They want that data. That's there, because that's what they're selling. They're packaging up they're packaging up you as an individual, everything they can find out about you, and they're selling to customers such as Peridua that wants to sell cars. You wonder why you get these little things in the mail, and you never bought a Peridua before, but all of a sudden you got a little flyer for a Peridua. And that's how they find out about you, right there. Why I'll get these various emails. I mean, these companies, and Google does the same thing, right there. You fill out these little questionnaires, your date of birth. That information is getting sold, right there. And that's just at there. And that's what big data is all about. You hear the term big data, and big data is gathering as much information as they can on individuals and selling it. A lot of people refer to as Big Brother from an old book, 1984 by George Orwell, where they talk about Big Brother knows everything about everybody. That their big data has basically said that that we want to collect as much information about everybody in the world as possible in order to sell it for various purposes and use it for mostly marketing. But sometimes law enforcement uses it. National Security Agency, which is a large, spy organization in the U.S. And short stories. When I was in the Air Force, I actually worked for NSA. I was one of their gatherers of information out there, so I know NSA. But their job is to collect as much information about everybody that they can in order to determine who might be a terrorist, a spy, a criminal. Again, law enforcement. The FBI does the same thing. I'm sure there's an equivalent in Malaysia that gathers intelligence on as potential bad guys. In the U.S., they actually gather information on about everybody, right there. I was told that there's a file about an inch thick on me, right there. And that was told to me by my brother, who works for Homeland Security. So he had access. He said he can't pull my file, but he knows there's one there on me. So that there, he knows about how big it is, but because he's my brother, he can't look at it. But again, because I used to have a security clearance, I worked in military defense, so I was also in the Air Force for 4 years. I was also in the Army Reserves for 5 years. So I've had advanced infantry training, I've had weapons training, I've had intelligence gathering. So I've had all kinds of classified training. Plus I worked in military electronics. I'm married to a foreigner. I'm living overseas. I've spent a lot of time overseas. I'm sure they're looking at me and what I'm doing. I'm a potential right there. Although I've been told by at least one FBI agent that was investigating one of my students that I passed the test and I'm clean. So, but again, I'm in the big data system right there. So as we get into byte measurements, I'm not going to worry too much about that. And how am I on time? I'm probably not going to finish, but I don't think we're going to meet Friday anyway. We're doing pretty well. Machine languages, we won't worry too much about this right here. When we write computer programs, right here, right there, we've got what's called machine language, and that's 1, 0, 1, 0, 1, 1, ones and zeros right there. And I programmed a machine language right there, where I flipped a bunch of switches, 8 switches, the ones and zeros, I hit the load button. I flipped the next switches, I hit the load button. I hit the next switches, I hit the load button. Then I enter a starting address and I hit the run button. And it goes through and looks at the program as a series of ones and zeros and runs the program. So, not a very efficient way to write code. Right there. Not a very efficient way to write code. You can also see it written in like A2 in hex numbers. You can also do A2 enter, A3 enter, A4 enter. This is when I first started teaching microprocessors. This is the way we wrote code. Was in machine code. We didn't do the ones and zeros anymore. We could do it in hex, but we still had to do it in machine code. The next level is that move into the number 35x. Move into B, the number 22x. Add A and B, and move to location 35x. That's a memory location. A right there. In other words, we store the result right there. This is assembly language. A lot easier than machine language, but still not very friendly right there. So now this might equate to 2C35. This might be 2D22. This might be 4C. This might be 7,835 right there. In other words, this is the machine code for that assembly language program. And the process of doing that is called an assembler right there. So we have assembly language right there. So we can write something in assembly language and have it translated into machine language right there. That was the first step. Again, when I first started teaching, we wrote things in machine language, either in hex or binary. normally hex. And we actually had an EEPROM programmer where you would write your code into that, burn a prompt, stick it into your system, test your code. Then we had the 8085, SCK85. We would enter the code into the hex like that there, and then we'd hit the start address and tell it to run the code right there. And then we got an assembler. We would write our code on the PC, run it through the assembler, and then download our code into our chip right there. We won't do that in this class. Painful way to learn programming right there. So we're going to use high-level languages right there, and almost 90% of code today is written in high-level languages, 95%. The only thing that is not written in high-level code is if you're writing embedded code for relatively small microprocessor-based tasks right there. If you're writing, say, the software to control a heating and air conditioning system for a low-cost PIC processor, you might do that in assembly language right there. But as soon as your heating and air conditioning got more complex, and it's for a whole building, you probably would switch to C right there. So high-level languages look remotely like the English language. Remotely like the English language. They're not quite English. And that's probably one of the reasons why most people in this class struggle with it, is because it's based on English. Almost all programming language is based on English, because languages were developed between the UK and the US predominantly So the Raspberry Pi is a UK product. The IBM PC, which is what all these computers are based on, is a US company right there. Google, which is who owns Android, is a US company. Apple, of course, is a US company. So, I'm not saying the US rules the world, but they definitely rule the computer programming world right there in terms of languages and that there. So, unfortunately, I realize that English, for some of you, is a struggling language. You struggle with it. That's there. I hope you're struggling enough to understand what I'm saying, but if not, watch the video or get help from your friends. But, I look at lab reports, and I can tell that most of you are not very proficient at writing detailed English reports. And I will say that you're better at it than I would be writing Malay reports. So I don't judge you, but I just know that writing in English is not your strongest suit. Therefore, now we're going to take you and ask you to write a series of detailed instructions in a language that's based on a language that you struggle with, that American students struggle with it at times. It's a double struggle. So I'm fully aware of what you're at there. But that's there. There is a difference between a compiled language and a scripted language. Java and PHP are what they call scripted languages, which means that they're not compiled into machine language. When we write a program in this class in C or C++, right there, the compiler will then take that program, convert it to assembly language, and then convert it to machine language. And when you run it on the desktop computer, it's 1s and 0s stored in memory. It's machine language. Java, on the other hand, is not compiled. The interpreter reads each instruction, figures out what it means, and then executes it. Compiled language is me writing a book and then having it translated into Malay, and you're reading the Malay version. You're reading it in the natural version that's there. A translated language means that here's a book, and as you read the book, you're running it through Google Translate that translates it into English as you're reading it, or into Malay as you're reading it. Interpreted languages tend to be slower because the translation process has to be done in runtime. Now, things written to run on the internet are typically written in JavaScript or PHP because you don't know what type of computer it's going to be run on the final end. Now, at one time, Apple used to use Motorola processors, which is now Freescale, and the Windows world all used Intel. Well, Motorola kind of, I don't know what should I say, they stumbled a little bit, and Intel got the Apple business. So now both Apple and Windows machines all run on Intel-based processors, right there. There are some AMD processors which are copycat Intel processors right there. But basically they're either Intel or Motorola, now they're Intel right there. But the World Wide Web and programs run on the World Wide Web might run on my Android tablet right there. They might run on, which uses a ARM processor. They might run on a iPad, which uses a different ARM processor that Apple itself develops. So you can't use compiled software over the web because you don't know what processor. And every processor speaks a different machine language. I didn't mention that, but machine languages are unique to a particular model and brand of processors. The exception is the AMDs and the Intels. AMD copies the Intel instruction set, so it'll run Intel code. Not 100% though, actually. But the ARM processor has a totally different machine language than the, i5, i6, or i5, i3, i7 Intel family. A totally different set of instructions than the the A5 processor that Apple uses in their phones, or A6 or A7. I don't know what model of processor they're on right now. They put an A in front of their processor, and it's actually an ARM base, but they make changes to it right there. So interpreted languages are scripts. In other words, do this, do this, do this. They're left in the script form, and then at the time you run the set of instructions, they're converted into machine language by the interpreter on that machine right there. So those are the three that we're looking at. We've got machine languages, assembly languages, high-level languages, and then scripted languages are actually a high-level language, but they're different than compiled languages right there. I think I'm going to stop at this point right there. Let's take this Friday off, okay? Spread the word that this Friday is going to be your Friday to miss. So the next 2 Fridays you will be here. This Friday we won't be, okay? So and I'll come in. That way I can only teach the 2 classes on Friday. We're just kind of rotated a little bit. Now there'll be some weeks that toward the end that I think I'll probably have to have all 3 classes, but I've actually talked about twice as long as I normally do for a first class. So So we get into C. I'm actually quite a ways from finishing 26. Oh yeah, there's a lot of slides on this particular first chapter. There's no way I was going to get through all right there. So we'll finish these next Wednesday then. And I'll just jump in next Wednesday. And again, the only way that I'm getting away with canceling Fridays is by going long on Wednesdays the week before, the week after that there. My normal class is actually, I talked an hour after I started recording.